Well, it's only 2 weeks till spring break, so that's, I guess, even better. Okay, yeah, so wanted to just wrap up Chapter 5 here with one additional example. This is not included in your notes, so there's a little extra space maybe on the last page there to add this on. But wanted to do one final example about sampling distributions to maybe sort of, I was hoping to do this at the end of lecture on Friday, so maybe this will be a good refresher for you here. Can you guys see the screen okay? I guess a little brighter. Is that okay? Okay, so extra example here. Suppose that we have information on the height of 5,000 female students here at Ohio State in inches. And we can summarize those heights using a histogram here. So here's our, everyone's clear on what a histogram is, yes? We're just tallying up the heights of these 5,000 people in one picture here. And it's very convenient that this works out, but from this histogram we can kind of see that the distribution of these people, these females' heights looks kind of like a normal distribution. So there's a green line superimposed, which is a normal distribution there. So if we let y equal the height of a randomly selected single OSU female student, we might say that height is normally distributed with a mean of, let's say, 63 and variance of 9. So again, where those numbers come from is just, we'll get to that more in Chapter 6. So I can ask questions something like this. This is exactly what we've seen before, even back in chapter 4. So what's the probability that a randomly selected female student is taller than 65 inches? So with y being distributed as a normal random variable with mean 63 and variance 9, 3 squared, I guess. I simply want the probability that y is bigger than 65. All right, this is just the usual thing. So to solve this, you can pick your favorite method. I'm going to do 1 minus the probability that y is less than or equal to 65. Then I can standardize. So it's the same as the probability that a standard normal is less than 65 minus the mean divided by the standard deviation, which is z less than or equal to 0.67. Okay, so it's just the usual thing so far. Then we've been sort of skipping over this step a lot, so I wanted to actually do it. So now if I want to know what the probability that a standard normal is less than 0.67, I need to go to the table, or if you want to use your calculator, that's fine too. So I'll go to the table. So I want 0.67. So I look for the 0.6 row over here, and I trace that over to the 0.07 column, and I see where that intersection is. That's right at 0.7486. So this is 1 minus 0.7486, or 0.2514. Okay, so this is nothing new. We've been doing this. You've been doing this a few times. You did it a lot in your homework, I think. So won't spend any more time on that. But now suppose we take a random sample of 5 female students. So now instead of looking at just one, we're taking a random sample of 5 of these students and compute the average height for these students. So what's the probability now that their average height is more than 65 inches? So let's set up some notation. So let's let y bar equal the average of 5 students. And what do we know about the distribution of y bar here? Who can help me out with the distribution of y bar? What type of a distribution is it? Binomial? Normal? Anybody else want to weigh in? Have another normal. Well, so remember that the individual distributions for the individual heights, just plain old y is normally distributed. So we know that the sample mean from this. So if I take a random sample of 5 students from this population, I know that the average is also going to have a normal distribution. So this is my sampling distribution that we looked at a lot last week. So it's going to be normal, and what's the mean of this thing going to be? Mu times n. So remember, y was distributed as a normal with mean 63 and variance 9. So if I was looking at the sum and not the average, then that would be n times mu. That's right. So if I'm looking at the average instead of the sum of all these things, yeah, same as mu. So the mean of the sampling distribution is the same as the mean of the original distribution, right? And what's the variance of this sampling distribution going to be? Exactly right. Yeah. So sigma squared over n. Sigma squared is 3 squared or 9, and n here is 5. So that's my variance. So this is the same mu as we had for our original distribution. This is sigma squared divided by n. So this here is that this is also mu. This is also sigma squared. Okay, so that's all kind of our setup here. So now I want to know the probability that the average height of these 5 students is more than 65 inches. So similar setup as before. It's probably that y bar is bigger than 65, which I'm going to do 1 minus. Probably that y bar is less than or equal to 65. And now my notation looks different. Right now I have a y bar instead of a y in there, but I know what the distribution of y bar is. I know that it has a normal distribution with mean and variance as given there. So I can do the same exact thing that I did before, right? So I can standardize. This is 1 minus the probability that a standard normal random variable. I can 65 minus the mean, which is 63, divided by the standard deviation now, which is the square root of 9 over 5. So 1 minus the probability of a z being less than or equal to 1.49. Okay, so I'm just standardizing the same way. Here is value of interest minus the mean divided by the standard deviation. So the standard deviation now is sigma over the square root of n, or square root of sigma squared over n, instead of just plain old sigma. So it's same standardization as we saw before. Just the standard deviation is different now. Okay. So now once I'm over to that last step there, I'm back in the usual case. I'm just using the table to find a standard normal probability. So if I can jump over to the table here, I want something about 1.49. Is that what I said? Yeah. So I come down here to the 1.4 row, trace that over to the 0.09 column, and find that number in the table is my probability. Is using the table, are you guys okay with that? I know we've been skipping over that a lot. I wanted to just make sure we all remember where those numbers are coming from. 0.9319. So this is 1 minus 0.9319 or 0.0681. Everybody okay with that? So just to point out that there's no approximations going on this slide, right? We're not using the central limit theorem. We're not doing anything like that, because the population, the individual student heights have a normal distribution. The sample mean has exactly a normal distribution. So there's no central limit theorem happening on this page. No approximations. Okay. Moving on now, suppose that I add into these 5,000 female students that I add in the height of 5,000 male students, so that overall I have 10,000, the height of 10,000 students, which I can summarize here in this histogram. So why does the histogram look like that? So if I have the height of men and women, why do I have this kind of a shape going on? Test your intuition. There's two variables, as in.
Like they're different, so you'll have like two almost distributions.
Yeah, right. So I have, females are sort of clustered around one height, and males are in general a little taller, which is why I have this shape going on. Yeah. Okay, and so and I can sort of approximate it using this red distribution. So so if I let x be the height of a randomly selected student out of these 10,000 people, it's going to be distributed as this funky-looking distribution here on the right side of the page. So we don't know what that is. It's definitely not normal, right? It's got two humps going on in there, and it's kind of weird. So that's my PDF for an individually selected person from this population of 10,000 people. So I don't know what the distribution is, but I can calculate, or suppose that I do know what the mean and variance of this thing are. So this is my mean mu, and this is my variance sigma squared. Okay, so I'm not saying anything about what the PDF is, although that's what the picture looks like, but I do know what mu and sigma are. Okay, so what's the probability that a randomly selected student is taller than 65 inches? So I want the probability that x is bigger than 65, right? Probability that a randomly selected student is taller than 65 inches. So if I want to kind of shade in on my picture on my PDF here the area that I'm looking for, the probability that I'm looking for. Again, what shaded area do I want under here? To the left or to the right? To the right, of course. So I want probability that my student is taller than 65 inches. So this here is the area that I'm looking for. This is the probability that x is bigger than 65. And I have no idea what that is. So you could, if I gave you the form of that PDF, you could integrate it and find that area. But for now, I don't know what that is. Yeah. So we'll leave a question mark there. So let's kind of take a similar strategy as before, though. Suppose now that I take a random sample of 5 students. What's the probability that their average height is more than 65 inches? So again, let's let x bar equal the average height of 5 students. Could be males or females now. And what do I know about the distribution of x bar? Do I know anything about the distribution of x bar? Well, I do know what the mean and variance of this distribution will be. So the mean of this thing, expected value of x bar, is going to be what? If I look at the original information, what's the mean of the sampling distribution? 67.5, right? Same as the mean of the distribution I'm looking at, of just the x's. And same for the variance of x bar. What's that going to be equal to? Oops. What's the variance of x bar going to be? 25 over n, exactly right. So the variance of this thing is always the variance of x divided by n. So here the variance of x is 25. Here n is 5. But I have no idea what the distribution of x bar is. Right? So if I want to know the probability that x bar is bigger than 65, I still don't know how to calculate that. So yeah. So in the case where we don't know what the distribution of x is, and our sample size is still small here, so we would just have five students we're looking at. I don't know how to answer this question yet. I sort of still can't do it using the techniques that we've used in this class. But if we jump up here, now I have a random sample of 50 students, and I keep asking the same question over and over. What's the probability that their average height is more than 65 inches? Now I can do something. Now we can use the results of the previous chapter to calculate this probability. So here is my sample size is 50. And again, let's let x bar equal the average height of 50 students now. So again, now remember we can use the central limit theorem with something we talked about last week if my sample size is bigger than 30. So because my sample size is bigger than 30, I can use the central limit theorem, which tells me that x bar is going to be approximately distributed as something that's normal. So when my sample size is smaller than 30, or especially when it's down at 5, I can't be sure that this approximation is okay. But when my sample size is big enough, bigger than 30 is what we're saying, then this approximation is okay. So in this case, it's going to have approximately a normal distribution, again with mean 67.5, and variance is going to be still sigma squared over n, so now that's 25 over 50. This is the same as before. Okay, and so now if I want to know the probability that x bar is bigger than 65, now I can do something about this. So take my usual strategy. This is 1 minus the probability that x bar is less than or equal to 65. Now I can standardize probability that x bar minus divided by the square root of 1/2 is less than or equal to that is okay. So I'm just using the same strategy, and now because x bar has a normal distribution, this thing over here, this is going to be approximately distributed as a normal 0, 1. So that's going to be approximately a z here. So it's 1 minus the probability that a z is less than or equal to negative 3.54. Okay. And now once we're down to here, we're back in our favorite boat where we can just go look at the table and find that probability. So I can flip over to the table. I want something about negative 3.54. So I try to find negative 3.54 on the table, and it's not there. Right? This smallest number I have over here is negative 3.49. So what's the probability that z is less than negative 3.54? It's pretty much 0, right? And in any case, it's less than 0.002. So when you get a number that's off the table, the probability of being less than that's essentially 0. So this is pretty much 1. So you're almost guaranteed that that average of 50 students is going to be larger than 65. Okay. So this example is meant to illustrate sort of when you can use the central limit theorem, or when you need to use the central limit theorem. I think in all of our examples, our sample size was always bigger than 30, but just in the case when the sample size is less than 30, you sort of, at least techniques we use in this class, sort of can't do anything about it. So you hope that your sample size is big enough to do this calculation. Questions, comments?
Yeah, why is it normally distributed with 0 and 1? Like, where's that?
Why is it distributed with 0? Yes, exactly right. So I have some space over here. So you remember that if that's a great question. So remember that if something is distributed as normal with mean mu and variance sigma squared, then x minus mu over sigma is distributed as a normal 0, 1. So again, you can imagine the normal distribution. If I'm subtracting off the mean here, I'm just shifting that distribution around, and then I'm scaling it so that it has a standard deviation of 1. So this thing, which we usually call z, has mean 0 and standard deviation 1, and still has a normal distribution there. That's a great question. So then when so then when x bar has approximately a normal distribution with mean mu and variance sigma squared over n, x bar minus mu divided by the square root of its variance is approximately distributed as a normal 0, 1. So same kind of things. Same formula, just my standard deviation is different over there on the other side. So that's a great question. Does that make sense? Okay. Yeah, Jamie.
Yeah, when we convert to the central limit theorem, do we introduce a percent error by doing that?
Great question. So when we convert to when we're over here, when we use the central limit theorem, do we incur some sort of an error? Yes, you do. So there is a big approximately distributed here, approximately distributed as, and there's no real way of saying how much that error is. That's why we want to make sure that the sample size is at least 30. When the sample size is at least 30, sort of the theory tells us that the error you'll get there is very, very small. So I could have used the same calculation for my smaller sample size, but the error there would probably have been a lot larger, and so it's sort of not safe in some way to use the approximation there. Yeah, so it's not very satisfying. Yeah, I can't tell you how much error you have, but the check of making sure the sample size is big enough ensures that error is going to be very, very small. Yeah, Andrew.
So if you have a value that's not on the table, can we just assume it's 1 or 0?
If you have a value that's a z value that's not on the table, like negative 3.54, can you assume it's 1 or 0? Yes. Make sure you have the right one of those. But if it's off the table negative, the probability being less than is 0. It's off the table positive, probability being less than is 1. Yeah. Good questions. Okay. All right. Well, that wraps up. It's going to wrap up chapter 5 for us. Let's forge ahead to chapter 6 here. And my computer's going to die. Okay, so hope you have your chapter 6 notes with you. Chapter 6, we're going to move on to something called point estimation. So just as a way of motivation, and I was talking to a few of you guys in office hours last week about this very question. So this is not listed in your notes here. We'll get to that in a second. But if you go back to any question we did in chapter 4 or 5, I don't know if you ever felt a little bit unsatisfied. So we asked something like, this was from our Chapter 5 notes, the time in minutes spent on hold for a customer calling a help center is exponentially distributed with parameter lambda equals 0.2. And then we said we had some sort of a random sample, IID observations from this distribution x1, x2 up to xn. So where did this thing come from? How did I know that lambda was 0.2? And maybe a bigger question is, how did I know it had an exponential distribution? That's more an assumption we'll make, but the issue is, how do I know that lambda is 0.2? And so this kind of leads us nicely into what we're going to talk about here in Chapter 6. So up until now, we've sort of assumed that we know what the parameters are. It was exponential with lambda 0.2. It's normal with mean 63 and variance 9. And any of the examples that we did, we've always assumed that we know what the mean is and the variance and some of those things. So we assume that we know what that, and then we kind of use that to explore various properties and calculate sampling distributions, calculate probabilities, all this stuff. And the point there was that we had not yet collected the data, right? So in the previous example we just did, I was asking you what's the probability that x bar, the sample of these 50 students, is bigger than 65. Well, I haven't collected information from those 50 students yet, so I don't know what their average height is. But I can use this theory that we know to kind of get an idea of what that might look like. So now now here in Chapter 6 and moving forward, we're going to kind of enter a more realistic situation where we're actually going to assume that we've collected some data and then use this data to estimate the parameters. So instead of just saying I know what lambda is or I know what mu and sigma squared are, I'm going to actually use information that I can collect to try to estimate what those things are. And that leads us to this idea of statistical inference. So this is now getting to the first page of your notes there. So this is kind of the foundational idea of statistics here is statistical inference, which involves I'm inferring something or I'm drawing conclusions about something that I don't know. So the parameters, I don't know what those are, and I'm drawing those conclusions using data that I collect. So I'm going to base my conclusions on sample statistics. So that can be anything really, but the main idea is I'm going to collect information and use that to draw a conclusion or make an inference about something that I don't know. And I'm going to use this symbol theta as a generic symbol for some parameter that I'm looking at. So that could be the mean, that could be the variance, it could be just some generic parameter that I want to know about. And so my goal is to select just a single number, so give just one number based on my sample data or information that I've collected that represents a sort of a good or a sensible value for what theta is. So here the idea is that we're going to use sample data to sort of make a best guess about what this thing might be. Sort of a best guess. About the value of this parameter. Okay, so just to make sure we're all on the same page terminology-wise, can talk about some definitions here. So we're talking here in this chapter about point estimation. So what is that? It's kind of what I'm more formally saying what we just said on the previous slide. A point estimate of this parameter theta is simply a single number that can be regarded in some way as being a good guess or a sensible value for theta. And I obtain that by choosing a suitable statistic and then calculating its value from the information that I've collected. So remember, a statistic, our formal definition of that is just it's a function of my data. So that could be the sample mean, it could be the median, it could be the minimum, it could be the maximum, anything that I can calculate from my data set that I have. And my selected statistic that I choose is called the point estimator of theta. So let's kind of very formally write out what these things are. So the parameter is, think about that, that's our true and unknown quantity of interest. And this corresponds to the population. So again, in general, the population is a very large group, and I don't know all the information about them. But so the parameter is going to represent my true quantity of interest. So we'll look at some examples of what that is. But the key idea is that it's unknown. I don't know what that thing is. So the estimator here is a statistic, and in particular, this is going to be a again, this is a function of my sample random variables. So to estimate that true unknown quantity, I'm going to use a statistic, which is what I calculate from my sample data, from the random variables that I have in my sample. And then, to be very picky here, the slight distinction here for estimator versus estimate is that the estimate is the actual calculated value that I get here. So this is the value of the statistic, and this is calculated for one particular sample. So calculated for one particular sample. And should also note that this will change, obviously, from sample to sample. So again, the estimator is a statistic, and we'll look at an example of this. But so a statistic that's like the sample mean or the sample median or something like that. And then the estimate is, so now we're going to assume that I have sample data and I can actually calculate the sample mean or calculate the sample median from my sample. But if I have one sample of people and I calculate the sample mean, for example, if I have a different group of people, I'm going to have a different sample mean. So that's the idea, that it'll change from sample to sample. So the notation here is, again, theta is our unknown value. And then we're going to use this generic theta hat. So it's a theta with a little hat on it. That's going to be that's what we're going to use for the estimator, or the estimate there. So if you see theta, that represents an unknown parameter. If you see a little hat on top of it, that represents an estimate. That's something that we calculate. So that sort of convention is to kind of like X bar. If we put some extra notation on the letter there, it corresponds to something from our sample. Okay, well let me do a quick example here to illustrate exactly what I'm talking about. So I think about a can of Planters mixed nuts. I could ask, what proportion of nuts in the can are going to be peanuts? So you always hope that there's more cashews in there, right? So here my parameter, sort of my unknown value here, what I'm interested in is the population proportion. And what I mean by that is the proportion of all Planters mixed nuts. So if I could somehow get every single container of mixed nuts and see the proportion of all those things that are peanuts, then I would know what this population proportion is. So that's corresponding to all planters mixed nuts here. Okay, so if I want to know what the population proportion is, sort of a very sensible point estimator here for this thing would be my sample proportion. And by sample proportion, I mean I can take just a single can of planters nuts and maybe count out the proportion of peanuts that are in that thing. So that's proportion of peanuts in a sample a sample of planters mixed nuts. And so I'm going to call this thing theta hat here. So the sample proportion is just, I take a sample of these mixed nuts and I actually calculate the proportion of peanuts that I have there. So the key difference here is that the first thing I'm not actually going to calculate that thing, right? I'm not actually going to look at the entire production line of planters mixed nuts and figure out the proportion of peanuts there. But what I can do is take a sample and calculate the proportion there. So it's kind of the distinction there. The population parameter, the population proportion, I don't know what that is, but I can go about calculating a sample proportion. That's something I can actually do. So then that's my point estimator. Then the point estimate is I take a particular sample and actually calculate what the sample proportion is. So the calculated value the proportion of peanuts in a sample. And we're also going to call this thing theta hat. Okay. So this is a very, very sort of basic example here of what these things are here in each of these cases. Questions you guys can think of? Is this, yeah?
It's kind of completely unrelated, but when do we need to down for the JMP like stuff?
When do you need to have JMP or jump? Not yet. That'll be more like chapter. Did we use that before? That'll be another few chapters down the road. I'll make sure to let you guys know when you should be getting that. Yeah, good question. Okay, let's do one more example here. Let's classic question of our lives here. How many licks does it take to get to the center of a Tootsie Roll pop? Has anybody ever actually done that? Of course, you can't do it, right? Well, so the parameter that I might be interested in is the average number of licks that it takes to get to the middle of the Tootsie Pop. Okay, and so that's again something that I don't know, right? I don't know what the true average. This is unknown. But I can set up an estimator to sort of get a best guess of what that thing is. And here this could be my estimator theta hat could be the if I take a sample of people who have actually done this, for example, this could be the sample mean. I could also use the sample median if I wanted to. And you could use anything else that you wanted to. I could use the minimum, I could use the maximum. There's lots of different choices, some of which are much better than others, but could use kind of whatever I want. But then suppose that I actually have this data, so those numbers there, let's say that's a bunch of people who have actually taken one lick at a time to get to the middle of this thing. So then I can actually calculate my estimate either theta hat for the sample mean I could calculate is 505.1, or if I use the sample median, I could use 539. And so the point is that I've calculated these things from my sample up above here. Okay, so the distinction there is the estimator is, I've chosen a particular statistic, and the estimate I actually calculate what the value of that thing is. Okay, so in this sort of simple case, I have two possible choices for what the average, sort of what the unknown truth here is about Tootsie Pops. I have two possibilities here, and I could have many more. Which one should I choose? So how to choose an estimate when I have more than one sort of reasonable option. So if I was asking you the average number of licks it takes to get to the middle of a Tootsie Pop, what would you tell me? You have several choices here, right? So that's kind of what we want to decide. We want to find ways of selecting a good estimate out of the many possibilities that we could use. Okay, so that's kind of the goal of this chapter, is to figure out how to choose good estimates when we have sort of multiple options. Questions, comments? Okay, so there's of the several criterion that we'll discuss, maybe just two in this chapter. This is our first criterion that we might use here, and that is this idea of choosing an unbiased estimator. Excuse me. So a formal definition here is our point estimator theta hat, we're going to say, is an unbiased estimator of theta if its expectation is equal to theta. So if the expected value of the estimate is equal to theta, then we're going to say that thing is unbiased. And so, of course, it could be not unbiased. It could be biased. In which case, we can calculate the bias. So that's just sort of the difference between what that estimator is expected to be and the actual truth. So that's my bias. So I have a few pictures here that are also in your notes there. Let's look on the left side here first. So suppose I have two estimators, theta hat 1 and theta hat 2. This is theta hat 2, theta hat 1. So what I'm saying is that the true value of theta is right there. So if you could imagine those things are normally distributed, you could see the expected value of theta 2 hat looks like it equals theta. It's centered right there at the true value. Whereas theta hat 1 is biased. It's off center a little bit there. Yeah.
I thought we said theta was unknown.
Yeah, great question. So I thought we said theta was unknown. Exactly right. So this is more conceptual here at this point, to say, just to kind of think about where this thing is going to be, where the distribution is centered. So in general, we won't know this. I'm just sort of trying to use a picture to illustrate kind of what this sort of looks like. But you're right, theta is unknown. We don't know what theta is. And the other picture is sort of the same thing. So bias just refers to, do we expect this thing to give us? Do we expect our estimator to give us the correct value? And so thinking about what we've talked about so far, and Jamie, this is what I was trying to put the picture. So it's unbiased if the mean of its sampling distribution is theta. So if you think about that normal distribution from before, if it's centered right at the true value, like that picture is, like theta hat 2 is there, then it's unbiased. So the main way you'll check this is to calculate the expected value of the estimator and see if that's equal to the parameter you're looking for. Okay, So let me do a few examples of this. Show you some examples of unbiased estimators. Let's say that we have a binomial random variable, so x is distributed as binomial np, and our estimate that we're going to use, our estimator is p hat, or you could imagine this is a theta hat, just the sample proportion. So I'm counting up the number of successes out of the total number of trials that I have here. Okay, so I want to know, so I'm trying to estimate, so I want to estimate p, which I don't know. So I'm trying to estimate the true proportion here in this binomial, for this binomial random variable. And so again, sort of the natural idea is to use the sample proportion. So let's see if we can let's see about the bias. See if our estimator is unbiased here. So the expected value of p hat. Well, that's just the expected value of x divided by sample size n. Okay, and I can pull the n outside. That's just like a constant there. So that's 1 over n times the expected value of x. And then what's the expected value of x for a binomial random variable? N times p, exactly right. Okay, so then the n's cancel out, and I do indeed have the expected value of p hat is equal to p. So maybe just formally write this out. The bias of p hat, which is the expected value of p hat minus the thing I'm trying to estimate, p, and that is the expected value is p, which is the thing that I'm trying to estimate. So this estimator is unbiased. So it's an unbiased estimator. Of the population proportion. Okay, so I can calculate, again, I don't know what p is, but I can calculate the expected value of my estimator and see if I'm sort of expecting to get the right thing. That's kind of the point of the bias here. Okay. Another example here, let's suppose that I have just a bunch of random variables, IID random variables, with some particular mean. So it doesn't matter what the distribution of those random variables are, as long as I know what their mean is. The sample mean here is we could call it mu hat or x bar. That's my estimate. So my parameter is mu, which is the population mean. And to estimate that, my estimator is mu hat, or I could just say x bar, which is the sample mean. Okay, so this is like if I want to know the average height of all students at Ohio State, that would be my population mean, for example. Then suppose I take a sample of, 10 students, 100 students, whatever, and calculate their sample mean. I could use that to sort of guess what the average height of all students at Ohio State is. Anyway, so now I want to see about the bias of my estimator here. So again, I'll take the expected value of x bar. Again, x bar is just the sample average, 1 over n times the sum of my individual observations. Again, remember, if I have the sum of if I have the expected value of a sum, that's the same as the sum of the expected values. So I can take the 1 over n outside and interchange the summation and expectation. So the expected value of a sum is the sum of the expected values. And this is all the xi's have the same expected value. They all have expected value mu. So if I take the average of n things that are all the same, I just get mu there. So again here, mu hat or x bar is indeed unbiased for the population mean. And let's just add on here. This is true for any this is true for any distribution. So whatever the distribution of my xi's are, doesn't matter. This is always, the sample mean is always going to give us an unbiased estimator of the population mean. Okay, the next example is a lot longer, so I think this is a good place to stop. Thank you guys so much for being here. We'll see you guys on Wednesday. Have a good rest of the day. Hey, Vanessa.
For my homework now, you said